Classification of elements and periodicity in properties. You might have visited library in your school. Have you ever noticed how books are arranged in the library? The various books are arranged so well in different shelves in the library, depending upon the class, subject, author, etc., so that one can easily find a book of her or his choice. Similarly, the various elements found in nature or discovered by scientists are classified and arranged in the form of a periodic table depending upon their characteristic properties. Let us throw some light on the distribution of these elements and their periodic properties in the module Classification of Elements and Periodicity in Properties. After reviewing this digital content, the students will be able to understand the need to classify the elements, brief the various attempts made by scientists de Bruijn, Newland, Lothar, Meyer and Mendeleev in classifying the elements. Describe the modern periodic table. Name the elements with atomic number greater than 100 according to IUPAC nomenclature. Explain the electronic configurations in periods and groups of modern periodic table. Learn the characteristics of SPDF block elements. List the properties of metals, nonmetals and metalloids. Recognize the periodic trends in physical and chemical properties of elements. Need to classify elements. The elements are the basic units of all types of matter. There are 118 elements known at present, and each element forms a large number of compounds. With such a large number of elements, it is very difficult to study individually the chemistry of all these elements and their innumerable compounds. Classifying the elements can help us to better understand the interrelationships between the physical and chemical properties of the substances. Genesis of periodic classification. During the 19th century, scientists began to categorize the elements according to the similarities in their physical and chemical properties. These scientists classified the elements in different ways. The end result of these studies was our modern periodic table. De Bruijn's triads. In the year 1829, Johann Wolfgang de Bruijn, a German scientist, was the first to classify elements into groups. He found that when elements were arranged into groups of 3 in the order of their increasing atomic mass, the atomic mass of the element which comes in the middle is the arithmetic mean of rest of the two. On the basis, he arranged these elements in one group, which is known as a triad. This arrangement of elements is known as de Bruijn's triads. De Bruijn's classification of elements was not very successful because of certain defects in it. A large number of similar elements could not be grouped into triads. Example, iron, manganese, nickel, cobalt, zinc and copper are similar elements but could not be placed in the triads. It was possible that quite dissimilar elements could be grouped into triads. Newland's octaves. The English chemist John Alexander Newland in 1865 propounded the law of octaves. According to the law of octave, when elements were placed in increasing order of their atomic mass, every 8th element showed similarity with the preceding 8th element in their physical and chemical properties. The relationship of Newland's octaves was just like every 8th note that resembles the first in octaves of music. There were few limitations in the Newland's attempt of classification, due to which it was not accepted. This classification was good with a few elements only and was not applicable to all elements. It was not valid for elements having atomic masses higher than calcium. After the discovery of noble gases, it became difficult to fit them in Newland's periodic table. Lothar-Meyer atomic volume curve. Lothar-Meyer plotted the physical properties such as atomic volume against atomic weight and obtained a periodically repeated pattern. Each fall and rise to a peak corresponds to a period. On the basis of his observations, Lothar-Meyer proposed that the physical properties of the elements are a periodic function of their atomic masses. By 1868, Lothar-Meyer had developed a table of the elements that closely resembled the modern periodic table. However, his work was not published until after the work of Dmitry Mendeleev. Mendeleev periodic table. In 1869, Mendeleev classified the known 56 elements on the basis of their physical and chemical properties in the increasing order of the atomic masses in the form of a table. The physical and chemical properties of the elements are periodic functions of their atomic masses. Mendeleev's periodic table contains 8 vertical columns of elements called groups and 7 horizontal rows called periods. Each group has 2 subgroups A and B. The properties of elements of a subgroup resemble each other more markedly than the properties of those between the elements of the 2 subgroups. Based on the positions in the periodic table, Mendeleev could predict the properties of some undiscovered elements. He left several blanks for elements that were not discovered at the time. For example, he left the gap under aluminium and a gap under silicon and predicted the elements as Aka aluminium and Eka silicon. Eka aluminium was later named as gallium and Eka silicon as germanium. With several merits of Mendeleev's classification, there were also few limitations of it. The position of hydrogen was not correctly defined. It was placed in group 1, although its properties resembled both the group 1 elements and the group 7 elements. In some cases, Mendeleev placed elements according to their similarities in properties and not in increasing order of their atomic masses, while some dissimilar elements were grouped together. For example, cobalt, atomic mass 58.9, was placed before nickel, atomic mass 58.6. Copper and mercury are similar in their properties, but were placed separately. Copper was placed in group 1, although it did not resemble the elements of this group. Isotopes have not been given separate places in the periodic table. Lanthanides and actinides were not given proper places in this periodic table. Modern periodic table. In 1913, Henry Moseley observed regularities in the characteristic X-ray spectra of the elements. A plot of N, where N is the frequency of X-rays emitted against the atomic number Z, gave a straight line and not the plot of N versus atomic mass. He suggested that atomic number is a more fundamental property of an element than its atomic mass. Modern periodic law states that the properties of the elements are periodic functions of their atomic numbers. The modern periodic table is also known as the long form of the periodic table. There are 8 groups which are further subdivided into 18 subgroups. The elements are arranged in the order of increasing atomic numbers in such a way that the elements with similar properties fall in the same vertical column. These vertical columns are referred to as groups. There are 8 groups which are further subdivided into 18 subgroups. There are 7 horizontal rows in the periodic table. These are called the periods. Nomenclature of elements with atomic number greater than 100. IUPAC has recommended rules for nomenclature of elements whose discovery is not completely proven and name not officially recognized. The nomenclature includes names which have abbreviations assigned for each digit of the atomic number, followed by the word EM at the end. Notation for IUPAC nomenclature is shown in the given table. Some examples for naming elements with atomic numbers above 100 are given on the screen. Electronic configurations in periods. The distribution of electrons into the orbitals of an atom is called the electronic configuration. Let us discuss the electronic configuration in periods and groups separately. Periods in the periodic table are arranged in such a way that each period reflects the valence shell that is being filled, the orbital in which the electrons are filled, and the number of electrons which are filled in each orbital. For example, for hydrogen, which has electronic configuration of 1s1, 1 means that first orbital is being filled, s tells us that s orbital is being filled, and superscript 1 means that one electron is already filled in s orbital, which can hold maximum of 2 electrons. Therefore, the first period n equal to 1 starts with hydrogen and ends with helium. The second part n equal to 2 starts with lithium and ends with neon. The third period n equals to 3 begins at sodium and the added electron enters a 3s orbital. Successive filling of 3s and 3p orbitals gives rise to the third period of 8 elements from sodium to argon. The fourth period n equal to 4 starts at potassium and ends at krypton with the filling up of the 4p orbitals. Altogether, we have 18 elements in this fourth period. The fifth period, n equal to 5, beginning with rubidium, is similar to the fourth period and contains the 4d transition series starting at trium, atomic number 39. This period ends at xenon, at xenon, with the filling up of the 5p orbitals. The sixth period, n equal to 6, contains 32 elements and successive electrons enter 6s, 4f, 5d and 6p orbitals in the order. Filling up of the 4f orbitals begins with cerium and ends at lutetium to give the 4f inner transition series, which is called the lanthanoid series. The seventh period, n equal to 7, is similar to the sixth period with the successive filling up of the 7s, 5f, 6d and 7p orbitals and includes most of the man-made radioactive elements. This period will end at the element with atomic number 118, which would belong to the noble gas family. Filling up of the 5f orbitals after actinium gives the 5f inner transition series known as the actinoid series. Groupwise electronic configurations. Elements in the same group have similar valence electronic configurations and have similar chemical and physical properties. For example, the group 1 elements, alkali metals, all have NS1 valence shell electronic configuration. Based on the type of valence atomic orbitals which are being filled, periodic table can be divided into 4 blocks, which are S block, P block, D block and F block. SP, D and F block elements. The S block elements include the elements of group 1 and group 2 with NS1 and NS2 outermost electronic configuration. These are all reactive metals with low ionization enthalpies. They lose electrons rapidly to form +1 and +2 ions. Metallic character and reactivity increase on going down the group. The P block elements belong to group numbers 13 to 18. These together with S block elements are called representative elements or main group elements. The outermost electronic configuration of these elements varies from NS2, NP1 to NS2, NP6. The elements of group 18 are known as noble gas or inert gases. The elements of group 17 are known as halogens and the elements of group 16 are known as chalcogens. The non-metallic character increases on moving left to right in a period and metallic character increases on moving down the group. The elements of group 3 to 12 are called the D block elements or the transition elements. The general outermost electronic configuration of these elements is N-1, D1 to 10, N0 to 2. These are all metals. These form colored ions and show variable valences and paramagnetism. These are mainly used as catalysts. The F block elements include 2 rows of elements at the bottom of the periodic table, that is, lanthanides and actinides. These elements are also known as the inner transition elements. The outer electronic configuration of these elements is N-2, F with electrons 1 to 14, N-1, D with electrons 0 to 1, metals, non-metals and metalloids. Metals are present on the left side of the periodic table. These are usually solids at room temperature. These have high melting and boiling points. These are malleable and ductile. Non-metals are present on the top right-hand side of the periodic table. These are usually gases or solids at room temperature with low melting and boiling points. Most of the non-metallic solids are brittle. Metallic character increases down the group. Non-metallic character increases from left to right in a period. Elements which show character of both, that is, metals and non-metals, are known as metalloids or semi-metals. Examples: silicon, germanium, arsenic, antimony, tellurium. Periodic trends in physical properties. Atomic radius decreases with increase in atomic number in a period and increases with increase in atomic number in a group. In general, ionic radius also follows the same trend. A quantitative measure of the tendency of an element to lose electron is known as the ionization enthalpy. Ionization enthalpy is always positive and is expressed in kilojoule per mole. The ionization enthalpy increases on going left to right in a period and increases on moving upwards in a group. Thus, alkali metals have lowest and noble gases have highest ionization energies. When an electron is added to a neutral gaseous atom to convert it into a negative ion, the change in enthalpy in the process is given by the electron gain enthalpy. The electron gain enthalpy increases on moving from left to right in a period and increases on moving upwards in a group. The qualitative measure of the ability of an atom to attract shared electrons from a chemical compound or chemical bond towards itself is known as electronegativity. It generally increases on moving upwards in a group. Electronegativity increases in a period from left to right. The given figure shows the trends of atomic radius, ionization enthalpy, electron gain enthalpy, electronegativity, metallic and non-metallic characters. observe the changes occurring. Periodic trends in chemical properties. The valence state, also called the oxidation state of an element, is usually given by the number of electrons in the outermost orbital or the value of 8 minus the number of electrons in the outermost orbitals. The valence states of the elements belonging to different groups are shown in the given table. Transition elements and actinoids show variable oxidation states. Another chemical property that needs to be discussed is the anomalous properties of second period elements. The first element of each of the groups 1, 2 and groups 13 to 17 differs in many respects from the other members of their respective groups. This anomalous behavior of the second period elements is attributed to their small size, large charge to radius ratio and high electronegativity of the elements. Periodic trends and chemical reactivity. In the periodic table, the chemical reactivity of elements is great at the two extremes. The chemical reactivity of the elements at the center of the periodic table is the least. Therefore, the chemical reactivity of the elements decreases and then increases as we move across a period. It is because the electron gain enthalpy of elements at the extreme right is the highest negative and the ionization enthalpy of elements at the extreme left is the least. Oxides formed of the elements on the left are basic and of the elements on the right are acidic in nature. Oxides of elements in the center are amphoteric or neutral. Let us summarize the main points covered in this digital content. Classifying elements can help us to better understand the interrelationships between the physical and chemical properties of these substances. Johann Wolfgang Dobrania observed that when elements were arranged into groups of 3 in order of their increasing atomic mass, the atomic mass of the element which comes in the middle was the arithmetic mean of the rest of the two. According to the law of Octaves, when elements were placed in the increasing order of their atomic mass, every eighth element showed similarity with the preceding eighth element in the